Hey guys, I'm I'm the rover lead of Technocrats Robotics, and this is our SDDR solution.
Hello, my name is Tushanjan Manta. I am the mechanical lead of Technocrats Robotics.
The newly designed rover chassis has been entirely manufactured using sheet metal fabrication, offering superior strength, lightweight performance, and easier maintenance compared to our previous builds.
The current robotic arm attached to the rover operates using a linear actuator mechanism, which has provided smooth and reliable actuation in past missions. However, the new arm currently being manufactured in-house represents a major leap forward in design and control. It employs a worm-driven stepper motor for high-precision angular motion and a DC-operated chain drive to transmit torque effectively while minimizing backlash. The state-of-the-art end effector at the tip of the arm is equipped with a differential gearbox, enabling synchronized yaw, pitch, and roll control for complex manipulation tasks.
Hello everyone, I'm the electrical lead at Technocrats Robotics. So this year for the IRC, we're coming up with a lot of new changes in the electrical department. For the first time in the history of Technocrats Robotics, we will be printing our own PCBs, which we have designed ourselves using KiCad software. So a few of the other changes are we're going to be using a much better processing power microcontroller. We're going to be using the STM F7 series and a few other changes which I'll show you guys. So this is going to be the base motors which we're going to be using. They are geared DC motors. They're controlled by these motor drivers. These are the Cytron 30 amp motor drivers. And for the arm connections, we'll be using these motor drivers. These are the Rhino 20 amp motor drivers. And powering the whole rover, we will have a 22 volt lithium ion battery. As for the control, this is the STM I've been talking about. This is the STM F7 series which we're going to be using this year. We are going to be changing from Arduino Unos and ESPs which we used last year to one single unified STM board. The STM's ARM Cortex chip gives us much better processing powers, and also one single board for the whole rover is going to help us a lot in many ways.
Hi, I'm Shoyadeep, the programming lead of Technocrats Robotics.
A rover uses encoders, an IMU, and an GNSS module for localization. The IMU and wheel encoders estimate short-range odometry, while GNSS provides global coordinates with accuracy under 70 centimeters. For perception, the rover uses multiple cameras and an Intel RealSense depth camera to capture 3D environmental data, detect obstacles, and understand terrain. It supports autonomous path planning and obstacle avoidance, allowing it to navigate unknown or uneven environments without manual control. ROS2 powers the navigation stack and runs SLAM for real-time mapping. By fusing data from all sensors, the autonomy system continuously estimates the rover's position, velocity, and surroundings for reliable autonomous operations. A rover features a 3+2 degree of freedom robotic arm designed for precise manipulation and sampling. It has 2 DOF in the main arm lengths for reaching and lifting, and 2 DOF in the end effector to provide wrist, yaw, and pitch for accurate object handling. The arm is moduled in URDF within ROS2, enabling realistic simulation and visualization of its joint motions. For control, it uses inverse kinematics to compute the joint angles needed to reach any target position or orientation, ensuring smooth and stable pick-and-place movements even in constrained environments. With URDF modeling, ROS2 control and IK algorithms, the arm can operate autonomously or via teleoperation.
Hi, myself Sharan Joshi, Astrobiology lead at Technocrats Robotics.
The central crosshair is the sampling point. Every frame the system reads that pixel, converts it to HSV, and matches the hue to a specific meaning. Red indicates higher carbohydrates, brown shows proline, orange represents carotenoids, yellow indicates phosphate, green suggests lower carbohydrates, blue highlights DNA presence, and violet represents proteins. The app instantly displays this information along with the detected color name. In the web dashboard, the system goes further. It breaks the color into RGB, HSV, and hex values and identifies whether it's chromatic or grayscale. It also keeps a short history of readings and turns them into live graphs. You get real-time RGB and HSV timelines, a radar chart of color distribution, averages, sample counts, and a color spectrum marking the current hue.
The rover is equipped to autonomously gather and analyze soil samples to support biological and geological investigation. The sample is carefully collected at a depth of 10 centimeters, and we ensure to follow the safety protocols during operations. To detect signs of biological activity, we use chemical tests designed like phosphate test to test potential extent life, diphenylamine test for nucleic acids, ninhydrin test to detect amino acids, proteins, and ammonia, Benedict test for carbohydrates. The rover sensor part provides data on soil and atmospheric conditions.
Hey guys, that's all for our SDDR submission. Looking forward to IRC 26.